start now, guys. Before I start on this, Holt's going to talk, and then we'll go over this real quick.
I hope you guys aren't too tired of me wandering up here. We're at the end of data collection. I wanted to say thank you for all of you from everything you've done. I know this has been a huge intrusion on a really busy class and a really demanding class. And I appreciate all the help with you guys sending emails, responding to the surveys, especially this final survey. There is about 25 people, and I don't really know who all they are yet, that haven't responded to that final survey. I'm asking that you do because in analysis we need to have matching up from pre-test to post-test to be able to see what was changed between you and between groups. So if you haven't, or some of your teammates haven't, we encourage you to do that. But most of all, I just want to say thanks. The preliminary analysis has just been phenomenal with this group. After 3 years, we're still finding new stuff of how to do things better, and it's because of the time you guys have taken to do that, and we really appreciate that. From everybody that's had to do the extra work on the PGVT lessons on, and so we really appreciate that. If you're one of those 25, please take some time to try and finish that last survey. Okay, thank you.
Great. Okay, today's lecture is going to be really quick. We'll probably get done in like 15 minutes or so. We're just going to go over this as an informal, non-judgmental raise of hands. Who looked over the stuff and read it? Good, thank you guys. So I'm just going to go over some of the main points that are presented here and answer any questions you guys have if I can answer them. There's no guarantees on that. So basically this Appendix A just talks about CFD, computational fluid dynamics, and some of the different methods of it and what it's good for and what you need to remember when you're doing it. So at the beginning here it says the computation of fluid dynamics involves replacing the partial differential equations with discretized algebraic equations that appropriate the partial differential equations. So it's kind of like FEA, where you can't solve the problem because there's too many partial differential equations and too many variables and all that stuff. But if you break it up into little pieces, you can solve it for each little piece, and that will approximate the solution. Same thing with CFD. So as we go down, talks about this stuff, and it talks about a couple different methods. So first I want to talk about in lab yesterday, and for those who have lab tomorrow, you're going to see that we use one of the three. We use the finite element style, and in this one there is you make a boundary layer and a mesh. Okay, so but the three types it talks about here. First is the finite element or finite volume style, and this one is kind of the one we did in class, where you make a mesh. You have the boundaries, and you have your object, and then the entire space is filled with a mesh. Both a boundary layer mesh and then the rest of the mesh, and we'll talk about that in a little bit. So that's the first one. That's the one that we're doing in this class. Some other methods are the boundary. Okay, thanks. So the other methods. The boundary element method, which instead of meshing the entire space, you just mesh the boundary around the object. So the thing is, when we mesh, like in lab, if you zoom in really close on the mesh that you create, you'll notice that there's a tet mesh in the whole filled space. And then there's also another mesh that's usually a hex mesh that's real thin. It's a boundary. It's a certain number of layers thick, and it goes around the object that the airflow is going around, because that's where you have a lot of boundary effects of the fluid flowing past it. And so, in fact, when you set up the mesh, there was a place where you told how thick the boundary should be. And I mentioned in lab yesterday it should be at least thick. That's a good, or at least 6 layers thick. That's the good rule of thumb to be able to model accurately. You want to have a layer about 6 thick. So that's the difference. So that's the difference between just the boundary element method and the finite element method. Is that they both have this boundary layer, but then the finite element method also meshes the rest of the space, whereas the boundary only focuses on what is that boundary right around the object. Does that make sense? Okay, hopefully. Finite difference method. Could you? Oh yeah, let's scroll up. So the finite difference method, it talks about the way it works is basically instead of having elements, you have points on a grid, kind of like in this illustration right here. I'll scroll down to get to it. So you have some points throughout the entire space, and the points can kind of move with relation to each other according to the flow around those points. So it differs from the element method because the elements stay in their place, and then this shows where the flow is through that element of space. And this one has points on the grid, and they kind of move a little bit. They don't all like flow past the thing, but they can move a little bit. So there's a little bit of difference. So we use the finite element. That's the one that we learned in this class. And you can do this for both two-dimensional and three-dimensional computational fluid dynamic analyses. All right, then we talk about, here it's talking about some of the crazy equations and stuff. So grids. So here it's talking about different types of grids or meshes. So there are structured grids or meshes and unstructured. The difference is structured are these rectangular grids. And so here's some example of those. And it's a uniform rectangular grid, the article says. And then unstructured is like this. It's use triangles or tetrahedrons if it's a three-dimensional mesh. This is for weird geometry, this is the simpler one. Tet meshes and triangle meshes are always easier. So this is the one we're doing in our lab. So there's those two types, structural and unstructured. And I believe, though, this is a small little thing, but the boundary layer, which would be right around the edge of this object, is usually rectangles. And if you zoom into your CFD that you're doing, you should see rectangles, I think. And then once you leave the boundary layer and it goes into the mesh, then it'll just mesh the rest with triangles. All right. So boundary conditions, you have to make sure you set up those right. Make sure the boundaries thick enough. And so it talks about, what kind of, boundaries you have set up. And then the article goes through some examples that are, I guess, cool if you want to spend the time to understand what's going on. There's another one. This is using the finite difference method with the points. And okay, so as we go down, now it talks about methodology down here. So here's another finite difference grid for a flow past a turbine blade. You can see it has a structured mesh around it. Okay, so methodology, it has this little chart thing here. So I want to talk about the application of CFD, which is down here. So advantages of CFD. Can someone give an example? Why is CFD so useful? What can we use it for? Matt.
It's for like complicated geometry you can't really calculate.
Right, exactly. That's a great thing. Jordan, you just want to say something?
So why do we do it? Like, why do we care about flow?
Mm-hmm.
Because especially if you're doing like something that's going to flow through a fluid, you want to calculate drag forces. And in industry, drag forces generally, respond to like fuel efficiency and things like that, stuff like that, and that's all in the cost.
Right. So flow is important, and it is part of the design process in many of the things that are designed today. So, you have something? Go ahead.
Yeah, I'm just going to say it's usually faster than building a model.
Exactly. It's faster and a lot cheaper than actually building a model, going to a wind tunnel, or renting time at a wind tunnel, because that's going to be huge costs. But if you can simulate all that on a computer, you can save a lot of time and a lot of money. So that's the huge advantages of CFD. Basically is that we can save time and money, and we can get these flow analyses that we want to do done cheaper and quicker. But difficulties of CFD, it's not perfect. And I like what the first sentence here. It says, one of the key points that a beginning CFD student should understand is that one cannot treat the computer as a magic black box when performing flow simulations. So you can't just kind of set up the problem and then say go and expect it to give a perfectly accurate result. It says it's quite possible to obtain a fully converged solution for a CFD simulation, but this is no guarantee the results are physically correct. So the lab that we did yesterday or we'll do tomorrow, in all honesty, may not be very accurate. I mean, we got a result that says that this is what it is here, and this is what it looks like. But then that may actually not be completely correct. So one thing that is done in industry is they want to calibrate their CFD to make sure it is reflecting accurate results. So they may run like a CFD analysis of something simple at a low speed or something, and then they do go to a wind tunnel with that object as well and do a real test on it and make sure the two match. And they'll tweak the CFD, their simulation and everything, like the slipperiness of the surface or whatever of their object or whatever they need to do until they can get their CFD results to match what's actually going on. Once they have that, then they know that they're getting accurate results, and they can start ramping up the speed and doing different things because they know it's now reflecting reality. So just out of the box, if you just run a CFD, it may not actually be reflecting reality. Does that make sense to everybody? Okay, are there any questions about that so far? Great. So that's what it kind of talks about here is verification and validation is that whole thing. You got to make sure that it is reflecting real results and not just what might be. But for the scope of this class, though, what we're doing is learning how to use the program, learning how to set up a CFD. And so what we have are generally good results anyway. We can use them for this class. So yeah, I like an example of the verification. I like the picture here. So this one shows, it says the upper half is a flow simulation experiment, and the lower half is from a finite difference calculation. So it looks like the upper half is a real result. This is what they actually did. This is what it looks like. And the bottom half is what the computer said, what the simulation predicted the result to be. And as you can see there, they're able to validate this and see that it is an accurate result. And so therefore they know that what they're getting is correct. So that's basically it. I'm just going to read the summary because it sums everything up. It says, in CFD, there are many different numerical schemes, grid techniques, etc. They all have their advantages and disadvantages. A great deal of care must be used in obtaining approximate numerical solutions to the governing equations of the fluid motion. The process is not simple as the often heard, just let the computer do it. Remember that CFD is a tool and as such needs to be used appropriately to produce meaningful results. The general field of computational fluid dynamics, in which computers and numerical analysis are combined to solve fluid flow problems, represents an extremely important subject area in advanced fluid mechanics. Considerable progress has been made in the past relative few years, but much remains to be done. The reader is encouraged to consult some of the available literature. So that's basically what the main point of CFD is. It's really useful. We can get a lot of stuff done with it. You just have to make sure you do it right. There are different ways to do it. We're learning one way to do it in this class. And if you want to learn more, it's a big field. You can do a lot with it. Are there any questions? Any last comments? All right. That's basically all I have. Thanks, guys.